In our last lecture, we have discussed what's Boolean algebra. We have discussed some of the theorems that are relevant, and also we introduced what is switching algebra. Just to recapitulate, what is switching algebra? Switching algebra is essentially a two-valued Boolean algebra. I mean, that way, say here we take the set B to be consisting of only two elements 0 and 1, and as you understand that if it has to be two elements, then it has to be, they are to be the identity elements, right. Therefore, B equal to 0 and 1, the two operators that we define, that plus is essentially we call it an OR operation, that is my, we call it say sometimes OR operation, that is my plus. Okay. We define the dot operations to be AND operation, right, and the complementation, another is the dash operation, which means that 1 dash equal to 0 and 0 dash equal to 1. This is complementation, right. Now, you can, if you check carefully, we will find that all of them will directly come, once we take 0 and 1, the identity elements to be the only two elements will come directly from the postulates and the theorems. Okay. Now, that is so far as our two-valued Boolean algebra, that means switching algebra, is concerned. Now, we will now assume the existence of what we call a Boolean variable, right. A Boolean variable, we represent it by x, y, say x1, w, like that. A Boolean variable is a variable which can assume either 0 or 1 value. That means it can assume either of the two, but not both, okay, at any instant of time. That is, that if we have to specify very I should say formally, then we say that x, if a Boolean variable, x is not equal to 0 if and only if x is equal to 1, and x is not equal to 1 if and only if x is equal to 0. Okay. This is, we will call such variables as a Boolean variable. Now, you can see that all the postulates that you have given and all the properties that you have given, that means all the theorems that you have given also, right, that they will be true for the Boolean variables as such. Okay. You can see it, prove it by means of perfect induction. By perfect induction, I mean that we take the values of 0 and 1 for all possible combinations of them and find it to be true, the left hand side will be equal to the right hand side, right, either by perfect inductions or by utilizing the postulates and the theorems that has already been proved. Okay. You can also see that all the postulates and the theorems will be true in terms of the Boolean variables themselves, right. Now, once we have it, right, now one thing is that from now onwards we will assume, okay, we will sometimes that use the term Boolean algebra and switching algebra a little bit interchangeably, but whatever we mean, will be meaning essentially that we will be dealing now onwards the switching algebra. Okay. Now, let us now define what is the switching expression. Okay. That the definition I will give is a recursive definition, right. The basis is this. A switching variable or constant is a switching expression. 2, if F1 and F2 are switching expressions, then so are F1 complement, F1 dashed, F2 complement, naturally the same definition wise, okay. F1 plus F2, F1 dot F2, okay. And the limitations that we give are that nothing else is a switching expression. You see that this is my basis, that is switching variable or constant is a switching expression. Now, if F1 and F2 are switching expressions, then so are F1 prime, F1 plus F2, F1 dot F2, and nothing else. This is the limitations that I say. Nothing else is a switching expression.
So not mentioning the third point and just mentioning the two.
That's right. In the case of the recursive definitions, you say what you get by recursions, and then you say that what are the limitations, okay, whether anything that you want to exclude or anything that you want to further include. Okay, that is why the third clause is always put in the case of the recursive definitions. Is it all right? Now, let's take a example. Just say, for example, xy plus yz plus say wxy bar. Okay, just to take an example, right? Now, let's see whether it follows the definitions of a switching expression or not. Now, let's take this. This is a switching variable, assuming that w, x, y, all of them are switching variable. If it's a switching expression, if it's a switching expression, then x dot y is a switching expression by definition. Okay, then x dot y is a switching expression. Similarly, y dot z, as I told you, that dot sometimes we will not put if we write two variables side by side. Okay, y dot z is a switching expression. If this is a switching expression and this is a switching expression, so is this a switching expression, right? Similarly, this is a switching expression, and so this entire thing is a switching expression. Therefore, you see that basically it follows a recursive definition of a switching expression, right?
So what is included in nothing else, sir?
I mean, come once more.
So what is included in nothing else?
No, I have said this. We say that whatever I defined by clause 1 and clause 2 are the set. I mean, I don't want to include anything more into it.
So can you give an example where we can get specific instance where something that has
not in the switching algebra. Now, this is the definitions of the switching algebra. Okay. Also, now let's see that let's take another example of it. Right. Say we can take it to be a switching function t. Say I take it, right? Now, once I write, so this is my W bar. Now, once I write that an expression like this, okay, now the values that expression assumes for different combinations of values of the variables, that means W, X, Y, okay, here 3 variables are there, defines a switching function. Should let me repeat once more. Let's say I have written a switching expression, this wxy plus w bar y plus x bar y. Okay. Now, this expression, okay, will assume different values, the values of ones and zeros, depending upon the different combinations of w, x and y that I put in. Okay. Now, the different values, all possible combinations of, for all possible combinations of values of w, x and y, right, and for each one of them, the value that t, w, x and y assumes, right, defines a switching function. Or in other words, we can say that switching function associates to each of the 2 to the power n combinations of that values of w, x and y, one element of the Boolean algebra. That means, say for example, if we say that b equal to 0 and 1, and w, x, y will have how many combinations of them? W, x, y. Since anyone can have a value of 0 or 1, there can be 8 combinations of them. For each of the combinations of w, x and y, okay, we associate one element from b, okay, that in fact defines a switching function. For example, let us take the situation w, x, y, right, and the function we write is f, okay, that is given by the switching expression, right. Say the different combinations that we can have is 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, okay, 1, 0, 1, 1, 1, 0, and 1, 1, 1. These are the 8 combinations that we have, 1, 2, 3, 4, 5, 6, 7, 8 combinations that we have, right. Let us see, I say that if w is equal to 1, x is equal to 1 and y is equal to 1, okay, the switching expression has got a value of 1, right, which means the function will have got a value of 1. Now, let us see w, x, y 1, therefore, here I have a value of 1, right. Now, w bar y, whenever w bar means when w is equal to 0, right, and y equal to 1, then we will have a, that expression will have a value of 1. Let us see w bar and y. W bar and y is this combination, therefore, we have a 1 over here, okay. W bar and 1 is combinations, this combinations is there, therefore, we have a value of 1 here, right. And let us say x bar y, x, which means x equal to 0 and y equal to 1, we should have a value equal to 1, right. Therefore, say x 0 and y 1, x 0, y 1, here I will have a value of 1, and x 0, y 1, we have a value of 1, which we already defined, right. Other places, it has a value of all zeros, okay. Now, you see the switching expression in fact defines for each of the combinations of w, x and y, okay, one elements, okay, either 0 or 1, right. Therefore, for each combinations of w, x and y, right, is associated with one element of the set b equal to 0, 1, right. Therefore, this defines what we call a switching function, okay, right. Acha. Now, one thing is, for example, let us see the situation. Another example let us take. Let us see that we take an example of okay. Therefore, say this is a switching expressions we have taken, right. Naturally, once more we can have 8 possible combinations of w, x and y, right? And immediately it defines a switching function, so to say. Okay. Now we have studied the switching algebra or the Boolean algebra, right? And the Boolean algebra gives us a method of manipulating these expressions to convert one expressions into another expression, right? Right. For example, let's see this expression we can manipulate to this way, that w bar x bar y bar, check it, I can from this and this I can take x and make it y plus y bar, okay, and plus say wx, right. Now this means that we can make w bar x bar y bar plus x plus wx, because y plus y bar equal to 1, okay, by rule of complement. This means w bar x bar y bar plus x, since x plus wx by law of absorption, okay, we can make it to be x, right. This is equal to, I can make it w bar x bar y bar plus x plus w bar, okay, x y bar, because this x plus w bar x y bar is essentially x once more, right. Therefore, I can this and this, if I can take now, I can have w bar y bar plus x. Therefore, you can see that this expression, yes, I have converted into another expressions which is equivalent, okay, w bar x bar y bar plus x y bar plus wx plus xy. These expressions I have converted into another expression which is an equivalent expression. Now, how do I prove that equivalence of these two expressions? I can prove the equivalence of these two expressions once more by means of the truth table, right. Let us, you can draw the truth table of these two and you can verify yourself that this truth table corresponding to this and the truth table corresponding to this will be same, okay. Yes.
So what's the difference between a switching expression and a switching function?
Therefore, basically a switching function is represented by means of a switching expression. It's okay. The switching expressions, what is a switching expression? Switching expression is nothing but to represent how, in an algebraic way, we represent a switching function. Right? The switching functions can be represented by means of a truth table as well. Let's take another example of it. xy x bar z plus yz. Okay, let's see. This we want to see that whether we can manipulate this. What we can manipulate to this? Let's say xy plus x bar z plus we can represent it as x plus x bar into z. Sorry, x plus x bar into yz. Okay. Now let's see this. I can say that xy plus x bar z plus xyz plus x bar yz. Okay. And this is equivalent to that we can now take, right, that xy, if I take this and this, xy 1 plus z, okay, and plus x bar z 1 plus y. Okay. This 1 plus z is equal to 1, therefore xy dot 1 plus x bar z dot 1, this is equal to xy plus x bar z. Okay. Now with you can see that if we now compare this expression with these expressions, you see that xy plus x bar z plus yz is essentially xy plus x bar z. This term is not necessary at all, okay, and they are equivalent. Therefore, what we can say that in that case, if we find that expressions are switching expressions like this, we can eliminate yz immediately, and this is called the rule of consensus. Okay, this is the rule of consensus. Now, if this is a rule of consensus, we should have at the same time another dual rule for this rule of consensus, and the dual rule is that x plus y, x bar plus z, y plus z, that should be equal to x plus y, x bar plus z. Okay, that's my dual rule. Okay. Now, I have not, of course, when I have computed this from, converted this from this expression to this expression by applying the rules of Boolean algebra. I have not said exactly what rules I have employed. I have not named them, but I think by this time you are familiar with the rules, and therefore you know that what rules I have applied. Okay, I have just shown the results of it, right? Now let's take another example, okay, where that we are using the rules of switching algebra to convert a switching expressions from one form to the other form. Let's the example be w bar x y bar plus say w bar x y plus w x y bar plus say w x y, right? Say this is the expression. Let's try to convert it into another form, right? One thing is that you can see that we can possibly combine these two, right, making w bar x y bar plus y, and possibly we can combine these two, right, w x y bar and w x y, right, giving me w x once more y bar plus y. Okay, this will be y bar plus y equal to 1. Therefore, w bar x plus, right, this is w bar x plus w x. You can see now that if we take x as common, this turns out to be w bar plus w x dot 1, this is equal to x. Therefore, you can see that such a big expression has been converted into, okay, that is expression like this, which is exactly x, right. Now, let's see the truth table of it and see that how the function comes, right. Say w x y, and let these expressions, we call it to be say e, okay, say 0 0 0 0 0 1 0 1 0 0 1 1 1 0 0. Now, w bar x y bar is which combinations? W bar x y bar, w bar x y bar is this combination. Therefore, for this combination, this is equal to 1, right. W bar x y, w bar x y is this combination for which this is 1. W x y bar is this combination, right, and w x y is this combination, they are 1. For other combinations, this is 0, this is 0, this is 0, and this is 0, right. And you can see that I have converted this by applying the rules of that Boolean algebra, okay, into this x. This essentially means you can see that whenever x is equal to 1, the expression, the function represented by this expression is equal to 1. Okay. Therefore, if you can see that this expression containing 4, so to say, terms, we call them terms, okay, can be converted into an expressions containing a single term with a single variable only, right. Now, this essentially what we call is a minimization. There should be a method for minimization. There are methods for minimization, okay, very systematic method. We will come to these methods afterwards. Okay. Now, we have so long given the definitions of Boolean algebra, given the definitions of switching algebra, right, and we have given the rules that came from the postulates and the theorems, so to say, and we have shown that what is a switching expression, how we can maneuver the switching expressions from one form to the other. Okay. Now, let us see some examples or some concrete things, some hardware where this switching algebra, okay, I can apply, right. One of them is you will be dealing with many times in your career is that logic gates, switching circuits with logic gates. Another is the same, I should say, that logic operations in terms of contact networks. Let's come first to the examples with logic gates, okay, that circuits with logic gates, right. Let us have the first, let me define some symbols of the logic gates, right. The first symbol that I will be defining is, and we call it an OR gate, a 2-input OR gate, right. This is an AND gate, and this is the complementations, or we call it the NOT gate, right. Now, they are 2-input OR gate means this, so to say, realizes the plus operation, this is the AND operation, and this is the dash or the complementation operations. We are talking about physical realizations. Therefore, 0 here, okay, the level is essentially a 0, a voltage which is a 0 level, right, and 1 here is a voltage which is equivalent to, which is a, say, +5 voltage level. But naturally, a physical gate, right, or physical level maintaining strictly at 0 is difficult. Therefore, we allow some tolerances. Possibly that 0 will represent a voltage from 0 volts to, say, 0.8 volts plus, right, and a 1 level, okay, or 1 will be represented by some voltages, say plus 2.4 volts to plus 5 volts. These are the levels we will maintain, right, which essentially means that in the case of an OR gate, right, the logic, that this logic plus 0, 1, 0, 1, this is 0, all were 1. That means, if any of the input is within these voltages, the output will be this voltage, right, otherwise output will be this voltage. In the case of an AND operation, right, if any of the input is this, then the output will also be 0, which means between 0 volts and, say, plus 0.8 volts. Otherwise, the output will be high, that means plus 2.4 volts to 5 volts. Okay. And in the case of a NOT, if we give a 0 here, the output will be 1. That means, if you give a low voltage here, the output will be high voltage, and if you give a high voltage here, the output will be low voltage. Therefore, this is the, I should say, physical realizations of the OR, AND, or NOT gate that we are talking of. Now, let us take an example, right. that let's take an example. So, let's say x1 x2 bar plus x2 x3 okay, plus x1 bar x2 x3 right. So, for example, this is a switching function f of x1 x2 x3 equal to this okay, and we are trying to making a realization of this right. Now, we can draw the corresponding circuit this way okay, that we have x1 x2 bar okay, here we have x2 x3 and here we have x1 bar x2 x3 right, all of them feeding to, so for example, and OR gate, and the output is my F okay. It's essentially a two-level realizations you can think of. You can think of that as if that we have a box like this okay, right. To this box we have an output F, we have three inputs say x1 x2 x3 okay. That x1 are once more the voltage levels depending upon the types of circuits or the types of elements that you are using right, types of logic we are using, x1 x2 x3 voltage levels. X1 is connected to here right, x2 is connected to here, and say if you want to that x2 say for example is connected to this point right, and to get x2 bar what we can have is this, we have an NOT gate and connect this x2 over to here okay. Here I am assuming that double rail inputs are not available, only x1 x2 x3 is available, and if I need to invert an x2 right, then we will have to invert x2 and put into over here okay. Now, sometimes what we will also assume is this, that along with x1 that x1 bar will also will be available, x2 dash will also be available, and x3 dash will also be available. In that case, these inversions, the inverter gates will not be necessary. I can connect x2 bar directly over to here right. Now, as I told you in my very first lecture, that our purpose may be that given a circuit like this is a simple circuit, there will be complicated and complex circuits right, that we have to tell that what is corresponding switching function right, write the switching function, and in fact convert it into what we call it sometimes a minimal representation of it, or sometimes given that specification we may have to come to the minimal circuit realization corresponding to the switching function okay. That will be one purpose of this plus right. Now, let us take this is a particular switching circuit for the logic circuit right, that we have given. It is a two level, by two level I mean that it has the first level and it has the second level, and such a circuit is called a two level circuit right. Now, also I have taken it is what we call it that sum of product, that means these are sum of these product terms. Essentially it is a sum of product form of a switching expression in the sum of product form, and that realization turns out to be a two level realization with an OR gate over to here at the first level, and then and set of AND gates at the second level, right. Let us take the corresponding another form of it, or the dual form of it, which we call that product of sum form, right, product of sum. In that case, for example, let us say that we have a function x1 plus say x2 bar, x2 plus x3, okay, right, and say x1 plus x1 bar plus x2 bar, okay. See, I mean a function like this I have taken, right, and the corresponding, you can see the corresponding realization, let the function be once more f x1, x2, x3, that means a function of 3 variables, right. The corresponding realization will be of this form, that we first realize x1 plus x2 bar by means of and OR gate, okay. Here I have x1, here I have x2 bar, here I have x2, here I have x3, right. x1 bar and say x2 bar, okay, and now put them into an AND gate, right. This realizes the function over to here. Now, here you see that in the first level you have an AND gate, and the second level here you have OR gates realizing this, okay, sum terms, and this realization is called the now, as opposed to the previous realization, which we call the sum of product, okay. In the case of a sum of product, naturally the first level is an OR, the second level is an AND or ANDs, and in the case of a product of sum, the first level is an AND and the second level are all ORs, right. Now, here also this is essentially a 2-level realization. Now, let us take another form of it, say I have taken another expression, and you can immediately see that it is no more in the 2 level, okay, right. That means it is neither sum of product nor product of sum, okay. Now, the thing is that let us realize it, okay, this way. Let us see, first we realize x1, x2, okay, this x3 bar, right. Therefore, I have realized up to this at this point, okay, this x4, and now I have realized up to this point, okay, right. Now, say once more, x3, okay, here you see that x2, x4 bar, that means I have x3, x5 just I have realized here, x2, x4 bar I have realized here. This sum I have realized here, right? Okay, and then I am multiplying this by x1 AND operation, and this entire thing now I am realizing by means of the OR. Okay, which means that say x1, x2 plus x3 bar I get here, dot x4 I get here, right? Up to this I have got here. Here x3, x5 dash dashed I have got here, x2, x4 dash dashed I have got here. The sum of them I have got here, this into product I have got here, and this sum I have got over to here. And you can see that the level, and this is where I have got the switching function f, which is a function of 5 variables x1 to x5, right? And the number of levels that I have used is the first level, this is the second level, this is the third level, and this is the fourth level. 4 levels I have given, right? And therefore, what I wanted to show is this, that we can have multi-level realizations, and a corresponding the switching function, the switching expressions can be a multi-level switching expressions as well. Okay, and let's stop here for time being. Will be
(1951). A young nation aspiring to find ways to fulfill a dream lays the foundation of an institution that will give aspiring technocrats the license to fly high. The first Indian Institute of Technology is born at Kharagpur. Founded on the basis of the recommendations of the NR Sarkar Committee that was set up in 1945 to consider the development of higher technical institutions in India, the institute was first established in 5 Esplanade East, Kolkata, before it moved to Kharagpur in 1951. With Sir Gyan Chandra Ghosh as the first director and Dr. B.C. Roy as one of its founding guardians, the institute established itself as the symbol of a young, dynamic and resurgent nation. As top students rubbed shoulders with the most celebrated of professors and scholars, visions took shape. And IIT Kharagpur continued to play the pioneering role that was envisaged for it, enabling India to become a knowledge powerhouse that it is today. At every stage of its evolution, IIT Kharagpur remained ahead of its times. It provided the best of facilities for the budding technologists, helping them shape their own as well as the nation's future. Indeed, today, IIT Kharagpur has blossomed into a time-tested, venerable institute of learning. With the rich experience of converting individuals into brilliant professionals through 50 glorious years. As you cross the campus gate, you feel the distinct nip that is IIT Kharagpur. The spirit of objective inquiry and lateral thinking hangs heavy in the air. The modern township-like campus of IIT Kharagpur, set in sylvan surroundings, is self-sufficient in all respects. From modern banks to the good old post office, from vast playgrounds and well-equipped gyms to modern auditoria and open-air theaters, and from the quiet fiber optic linked residential quarters for the faculty to the web-enabled hostel rooms for the students. At IIT Kharagpur, lush green bowers of tranquility coexist with smart cards and ATMs. Spread over 690 hectares of sprawling cyber habitat, 120 kilometers from Kolkata, IIT Kharagpur is one of the largest network campuses in Asia. Just the academic complexes itself spreads over a built-up area of about 2 million square feet, of which 150,000 square feet is the new complex that commemorates the Golden Jubilee celebrations. And that's not all. It is the only IIT to have conquered territory beyond its own through cutting-edge courses offered in its extension campuses at Kolkata and Bhubaneswar. IIT Kharagpur is not just about its large campus, but its diverse range of activities. It offers the widest spectrum of disciplines, ranging from aerospace, biotechnology, cryogenics, to architecture, mining and agricultural engineering, supported by strong faculties of sciences, humanities and management. There are more than 30 departments and centers that offer the largest number of undergraduate and postgraduate courses amongst the IITs. The courses are ever evolving and show the way for other sister institutions. The richness in its diverse activities is showcased by the technological support the institution provides in areas like architecture, agriculture, post-harvest technology, and medical sciences. The institute has revolutionized and popularized rice milling technology. The other major contributions of IIT Kharagpur have been in the critical fields of defense, railways, space research, power systems, and petrochemicals. All these activities directly empower the human requirements of the nation. Advanced facilities at the Institute make it possible to undertake cutting-edge research and service-sponsored research projects. The array of equipment ranges from aerodynamic testing laboratories to intelligent machining centers, atomic spectrometers, to VLSI design labs, molecular beam epitaxy, to anechoic chamber, fast protein liquid chromatographs, to liquid nitrogen plants. The cutting-edge technologies are at par with the best research facilities across the globe. In fact, the volume of research and development activities at the Institute is incredible. In terms of the number of patents it owns, the volume of industrial consultancy it provides, and the revenue that it earns from all these make IIT Kharagpur a class apart and strengthens its position as the true pioneer in technological education in India. The Institute Library deserves a special mention. Fully web-enabled, it is one of the largest in Asia with over 324,000 volumes of material, including books, videos, microfilm, and patent documents. ingredients that ensure a student's mind develops at the right pace. Along with its strong sense of academics, which is ensured by a strict selection process, life at Kharagpur is a celebration of, well, life. And at its heart are the students. In fact, the saying goes that you can take an IITN out of KGP, but not KGP out of an IITN. You've left a part of you behind. For most of the students, life in the campus was in itself a festivity, a collage of activities that shape their mind and body, a collage of events that was a synthesis of competition and cooperation, a collage of interests as diverse as dramatics and ham radio. Yes, life at Kharagpur has always been exciting, and the years cemented lifelong bonds as lives mingled over cups of joy and stretched over stimulating semesters. The halls, with their blocks and wings connected by charming catwalks, remain ensconced in their own world. A collage of memories. Infrastructurally adequate, architecturally meticulous, and holistically inspiring, where students, wherever they might be from, invariably come into their own, developing their individual talents, honing their skills to take on challenges with confidence, so they can move ahead in fulfilling their dreams. What makes IIT Kharagpur so unique is its environment. Undiluted by the diversions of metropolitan surroundings, the close-knit campus life enhances the entrepreneurial and innovative spirit of the achievers-to-be. In an environment that is so stimulating, it is only natural that down the years, IIT Kharagpur has consistently produced well-rounded individuals. Many of them are celebrities in their own right. Holistic grooming has had a lot to do with this. So, no matter which walk of life they choose, the IIT KGPite stands tall. And so does the institution that bred him, in majestic splendor. The alumni of this institute command global respect. Their distinguished presence at the helm of global giants is a matter of national pride. For the students of IIT Kharagpur, it is impossible to erase any scratch of memory about their alma mater. In fact, some come back to invest sentiment, pride, and money, to see the institute they call home rise to even greater heights, structurally, functionally, as well as holistically. Their singular aim is to make IIT Kharagpur an institute whichever way you look at it, par excellence. A man's journey into quiet accomplishment and the Hall of Fame starts with the right step. And the training and placement cell of IIT has been the efficient facilitator in this regard for over 30,000 graduates. Having placed more than 95% of its students in a wide range of industries consistently for over 2 decades, It is no wonder that the institute is the most preferred campus for technical recruitment of quality manpower. With infrastructure like industrial power and communication facilities, in addition to its excellent research and consultancy facilities, STEP, or Science and Technology Entrepreneurs Park, aims to assist the budding entrepreneur into a successful adventure capitalist, guiding him right from the concept, institutional financing, production, leading up to the launch and marketing of the product. With its rich pool of talent and excellent infrastructure, it is no surprise that through the last 3 decades, IIT Kharagpur has developed strong liaison with the industry. SRIC, or Sponsored Research and Industrial Consultancy Cell, was formalized as the Special Industry Interaction Cell in 1982. Devoted full-time to handle industrial projects and consultancies, and for deploying and propagating intellectual property. Successful sponsored research projects straddle a wide spectrum, ranging from computers, communication and biotechnology to robotics, photonics, and food processing. The setting up of a state-of-the-art VLSI CAD laboratory and tie-ups with GE in areas ranging from vehicle structure design to electrical communication and software technologies are excellent examples of IIT Kharagpur's ever-evolving pioneering spirit. Collaborations with a host of national and industrial majors are a testimony of its proven expertise and research repertoire. Indeed, in this golden jubilee year, as the celebration continues, Pandit Nehru would surely have been a proud man today. For him, IIT Kharagpur was always more than just an institute of technology. In his own immortal words, it is indeed a fine monument of modern India.